Hi, here I'm doing the second piece of proof about this big theorem on uniform integrability and LP convergence. So here was the theorem we're talking about. So if we have improbability convergence, then we have these statements here. One of them is LP convergence, the other is P power uniform integrability. And we have seen in the previous video how to prove that 1 implies 2. Now I'm going to do 2 implies 1. Okay, so I'm going to do this now. 2 implies 1. Okay, so we are assuming uniform integrability and we want to show LP convergence, and we're also assuming, of course, improbability convergence. So I'm going to start proving 2 implies 1. I'm going to start, again I'm going to do things for p equals 1 for simplicity, and I'm going to start with the cutoff function. Cutoff function, which I'm going to call phi, and it will have a nice index k, and instead of formalizing it, I'm just going to draw you what this cutoff function looks like as a function of x. So it is going to be the identity function between minus k and k. Okay, so just identity here, and then it's going to freeze. So it's going to stay at level k whenever x is larger than k, and it's going to stay at level minus k whenever x is smaller than minus k. That's my cutoff function. Okay, and I want to make a few remarks on this. The first remark is that this function is of bounded slope. Phi k of x minus phi k of y is never larger in mod than the distance between x and y. So the slope of this function is bounded by 1, of course. Okay, that's clear. The second thing I want to make, second observation I want to make, is that phi of k of x minus x mod is bounded by x times the indicator that x mod, well, x mod times the indicator that x mod is larger than k. Okay, that's another simple observation. So why is that? If x is between minus k and k, then phi of x is just identity. So phi of x minus x is 0. When x is outside this range, then if it's outside to the right, then the indicator is 1, x mod is x mod, phi is just k, so k minus x under the mod is clearly smaller than or equal than x mod on the right, and in a similar way it's smaller than or equal to x mod on the left as well. So that's 2 simple facts about this function, and we're going to use these for for proving LP convergence, L1 convergence actually. Okay, so let's start with the actual proof. So uniform integrability. What is uniform integrability? Here is the definition. P is power uniform integrable. P is 1 for this proof if the expectation of x mod under the indicator x is larger than c is 0 in the limit, even if I take a supremum here. Okay, now notice that I have something very similar at this point. So I have x mod, indicator x mod larger than k. It's very similar to what we have in the definition of uniform integrability. So that's why if I now look at the expectation of phi k of xn, so xn is my random variable xn, okay, minus xn, that is, in fact I'm gonna put a mod here, I want a mod here, that is, according to the previous line, bounded by expectation of xn mod, indicator xn mod larger than k, and that's exactly the thing that even if I take a supremum of, will go to 0 with this bound k. So I'm using k here rather than c. So this will go to 0 even if I take a supremum. In other words, if I want this to be smaller than epsilon third for every n, even taking a supremum, can work if I pick k to be large enough, which I'm going to do. Okay, so pick k large enough so that by uniform integrability, the difference between phi k of xn minus xn for every n all n at the same time is larger than epsilon. I want a third here, not an epsilon, epsilon third. I want epsilon third. Okay, right. So that's the first observation. Now the second observation is a lemma we had before, and that's lemma number 2 here, which says that for any L1 random variable there is an epsilon, so that for any L1 random variable every epsilon there is a k, so that I can make this expectation smaller than epsilon, and I'm going to apply this again on that function here. So by lemma 2 tells me that there is a k large enough so that if I take the similar thing on x, the limiting variable, rather than xn, then this can be made smaller than epsilon third, again if k is large enough. So if k wasn't large enough in the first step, then I enlarge it to make sure that both of these are satisfied. Okay, remember that we're looking at the original theorem, so we're looking at a limiting variable x, and that's the thing I'm putting in here. Okay, and the third observation is, that's an easy thing to check, that phi is continuous. And in fact, that's not enough. I think we need this property here. We need this property here. So phi has this bound here, and it's easy to conclude from that phi of k of xn converges in probability to phi of x. So xn converges in probability to x. That was the assumption of the big theorem. And if you apply a function that has this bound, you can easily transfer the improbability convergence to the convergence of the phi of k values of xn to the phi of k value of x. Okay? So now, here is something which you should believe me, I didn't prove dominated convergence theorem under this weaker condition. We proved dominated convergence theorem under sure convergence, and I think it's probably easy to see that it still works under almost sure convergence. In fact, there is a version of bounded or dominated convergence theorem which works with improbability convergence. And so, since phi k of xn mod is of course always less than or equal to k, because this function never goes above k or below minus k, this is level minus k and this is level plus k, right? So it never goes higher than that or lower than this. And therefore, there is a version of dominated convergence which works with improbability convergence, and you can actually pass this improbability limit out into a limit on expectations, and that tells you that you can pick a large enough n. Once you fixed k, you can pick a large enough n so that phi of k of xn minus phi k of x in the mod and in the expectation is less than epsilon third. You can certainly do that. You can certainly do that in this improbability sense, and now you have to believe me that dominated convergence, so this is dominated convergence. Dominated convergence, take this limit out from inside the expectation, and the expectation, the L1 distance between phi k of xn and phi k of x also converges to 0. In other words, once k is fixed, one can pick a large enough n so that this is true. And now we can finish the argument. So what we want to do is L1 convergence, right? Notice that we want to prove 2 implies 1, so it's L1 convergence. And so what we're going to do is just start writing up what that means. We want to show that expectation of xn minus x can be smaller than epsilon just by picking large enough n. And so we already picked large enough n for that. And let's see how that works. So again, a triangle inequality. I'm going to insert a couple of terms here. I'm going to add in a phi n of xn. and straight away I'm going to apply triangle inequality on that. Okay, so I added in phi n of xn. Of course I need to subtract phi n, oh sorry, this is phi k of xn. Phi k of xn. Of course I need to subtract that, so I'm going to subtract phi k of xn, but I'm going to add in a new term as well. I'm going to add in phi k of x, and then subtract phi k of xn. Okay, so now I added in phi k of x, I need to subtract that, so I'm going to subtract that, and I'm also going to write in x here. Actually I swapped around signs, but okay, I'm going to explain this in a second. So let's just write here phi k of x, okay, minus x, and it's all in the mod. Alright, so let me explain what is actually happening here. So what is happening here is that I wrote this difference as xn minus phi k of xn plus phi k of xn minus phi k of x plus phi k of x and minus x. Clearly I didn't do anything because I subtracted phi k of x and I added it back. I subtracted phi k of x, I added it back. But then when I group these like that and I apply a triangle inequality on these terms, that's how I get the first term, which is this difference, the second term, which is that difference, and the third term, which is that difference at the end. Okay, so this is what's going on. And now I'm done because all of these terms are smaller than epsilon third. The first guy is here, smaller than epsilon third. The second guy is there, smaller than epsilon third. You just swap it around, but that doesn't matter in the mod. Okay, the last guy is there, again smaller than epsilon third. So all of these guys are smaller than epsilon third, and that means that this whole thing is smaller than epsilon. So what happened is I picked an epsilon, and I can pick k for that epsilon, and then for that k and for that epsilon I can pick n large enough so that all of this holds. In other words, I picked epsilon, I pick n large enough so that this holds. That exactly means L1 convergence. So I did prove that under the improbability assumption and under first power uniform integrability, I do have L1 convergence. So the proof for p equals to 1 is done.